of chemistry. Now I would like to introduce the teams to the judges. So judges, the rightmost team is the team IISc. After that there is the team IIT Bombay, then IIT Delhi, and at the leftmost position there is IIT Kanpur. Now I would like to introduce our judges for the deep thought for chemistry. Our judges for this session are Dr. Anirban Hazra and Dr. C.V. Ramana. Dr. Hazra is an associate professor at the Department of Chemistry, IISER Pune, specializing in the domain of theoretical chemistry. While his research deals with the chemical transformation in the excited state, he has a profound interest in science education. Please have a great round of applause for him. Dr. Chepuri Venkata Ramana is a scientist at Organic Chemistry Division, CSIR National Chemical Laboratory, Pune. He designed novel catalytic strategy for the total synthesis of natural products and the active pharmaceutical ingredients. Please have another great round of applause for him. I would like to thank them for being present here as the judges and also being present during the framing of the questions. Now, for the judges, audience, and our participants, I will briefly go through the rules and the guidelines for this thing. So, this deep thought will be 2 hours per subject. There will be 4 questions for chemistry. There will be one cheat system by which one team is the directed team that will be chosen for the first thing. They will choose one question. They will get 15 minutes time for presentation and the thinking time. In this 15 minutes, they have to present and think both. After that, the question will be passed on to the next team in the pre-decided order. That they will get 2 minutes. After that, both of the team will give 1 and 1 minute in the order. The marks distribution for the first team will be they can get 20 marks if they are fully correct. After the first passed on team can get 10 marks if they are fully correct. After that, the both of teams can get 5 marks each if they are fully correct. After this 19 minutes end for the presentation and the thinking of all the teams, there will be around 5-6 minutes for the judges in which the judges can ask their doubt, ask for the clarification if they need any. After that, our QMC will come and explain the answer. I request our judges to have the clarification after everyone present the question, so that they won't get that their time won't get disturbed, and also they won't get any hint by your question. Also, the teams are advised not to answer the repeated answer which the previous team already presented, because that doesn't have any marks. Any decision made by our judges and the QMCs will be final. There won't be any debate on that. The time will start if the first team time ends, then immediately the second team time starts, and that there won't be any time lag. Now I hand over the mic to our podium coordinator, that is Aditya and Johan.
Good morning, everyone. Welcome to Chemistry Deep Thought. My name is Aditya and he is Johan. I'd like to thank the judges, Dr. Anirban Hazra and Dr. C.V. Ramana, for being a part of this event. So firstly, I'd like the judges to pick up a cheat, which will be provided by Johan. IIT Delhi gets to pick the first question. Which one are you going to pick? Inky Pinky Pong. So here is a question. Sonal, an industrial chemist, synthesized the xanthine derivative A as an attempt to create a new artificial textile dye. On treatment of A with phosphorus oxychloride, the compound B was obtained, which afforded compounds C, D, and E. On treatment with hydrazine, 2-amino-imidazole slash triethylamine and 2-methyl-imidazole slash triethylamine respectively. Give a plausible mechanism for the synthesis of A in the scheme given below. This is the first question. The second question is, give the structures of B, C, D, and E. The mechanism, scheme is given below. Sonal observed that A is pink at pH 5 and turns colorless when the pH is increased to 8. Question number 3. Give a plausible reason for the observable reversible color change with varying pH. Next, Sonal experimented with adding 10 micromolar aqueous solutions of Cu2 plus and Ag2 plus salts to 1 millimolar acetonitrile water solution of C, D, and E maintained at pH 5. On adding Cu2 plus solution to the colorless acetonitrile water solution of C and D, both the solutions turned pink within 1 minute, but adding Cu2 plus to E did not lead to any color change. However, addition of a Ag2 plus salt to the solution of C and D led to a pink color appearing only after stirring for 50 hours. Puzzled by the observations, Sonal measured the absorption spectra of A, C, and D at pH 5. She found that A has an absorption maxima at lambda max 490 nanometer, while C and D have absorption maxima at lambda max 320 nanometer and 345 nanometer respectively. After 1 minute of adding Cu2 plus to C and D, another peak appeared at lambda 498 nanometer. Question number 4. Helps Sonal explain why the neutral solution of C and D turns pink after addition of Cu2 plus. Also comment on why Ag2 plus takes more time for the color change than Cu2 plus when added to the aqueous solution of C and D. Give a plausible reasoning to explain why addition of Cu2 plus to E does not lead to any color change while D turns pink. So IIT Delhi, do you have any questions? Okay, so your time starts now. 5 minutes left.
Yeah, so in the formation of C, the isocyanide reaction is happening. So an amide is formed along with the methyl cyanate. And the difference in D is that this NH2 is replaced with NC, and in E, N double bond C double bond O, isocyanate is formed. And for B, that is COH would be replaced by COCl due to POCl3, and the mechanism is a formation of A is two simultaneous electrophilic aromatic substitutions followed by two dehydrations in the acidic media.
We think that the pink color of A in acidic medium is due to an attachment of H to the nitrogen of ET2 here. So in acidic solution, this must be becoming NH plus, but in neutral or basic solution, that is not the case. So that might be the reason for pink color. And for when reacting with Cu2 plus and Hg2 plus, the isonitrile would be reacting with them as these salts are, as these salts can form, and CuNC2, formation of CuNC2 would be more favorable than HgNC2 due to, and so we see a faster reaction for Cu2 plus compared to Hg2 plus. But in E, there is no such isocyanate group, so Cu2 plus and Hg2 plus cannot react with it.
Cu2 plus has a higher electron affinity, like it has more affinity towards ligands. So that's why.
30 seconds, Sylvain.
Pink color is due to formation of a complex.
In part 3, the pink color is due to the formation of complex.
Time's up.
Okay. First off, the reaction that produces B would be the transformation with the production of an acyl chloride group, COCl, and then further on when we add NH2NH2, it becomes an amide, which is also the same in D, whereas in E we produce a cyanide group. It's fine. So Hg2 plus takes more time for the color change because Hg2 plus is a bigger ion, and as we can see the groups are very big, so because of steric hindrance it might be that the reaction occurs at a slower rate. Okay. That's pretty much.
Time's up.
Okay, so for the third part, where at pH 5 pH it is pink. So it is pink color due to the conjugation in A molecule, and when the pH is increased, like there is no positive charge on the N plus at higher pH, and as a result the conjugation breaks, and for that we do not have the pink color that we had earlier. For the fourth part, on adding Cu2 plus, there is a complexation reaction. There is a bidentate ligand, and that forms a complex with Cu2 plus, which gives the given color. Also, Ag2 plus has a lower complex formation tendency than Cu2 plus. As a result, it takes more time to form the complex, and yeah. Yeah, so and for the fifth part, E does not actually form complex with Cu2 plus, due to which we do not get the same color, like the pink color.
Time's up.
So for the first and the second part, he's drawing the compounds on the board. For the third part, Cu2 plus and Hg2 plus, both of them form complexes with isocyanide. But Hg2 plus has lesser affinity to forming a complex compound, and so it takes more time. The copper Cu2 plus forms it quickly. And the explanation to why why E does not lead to any color change while D turns pink is because there is no Cn minus available with compound E, because it is forming an isocyanide as they have drawn right here, and so that is why there is no color change.
Yeah, time is up. So I'd like to ask the judges if they have any clarifications for the team.
IIT Delhi, do you write the structure of isocyanate? You said cyanate is forming, no? IIT Delhi.
Yeah. So what's the question? Could you please repeat?
The structure of cyanate.
Cyanide.
Whatever you wrote. Cyanide.
E. Are you talking about E?
No, see, in this, you have drawn the structure of B. Can you also draw the structure of C clearly?
Okay.
That's C.
Yeah.
Okay, and D?
And D would be
side products would also be formed, right? With
No,
this.
so just write the structure of C and D very clearly. So C you have written now, correct?
Okay.
Okay, now write D.
D is also the same.
D is what?
D is it's the same.
D and C and D are the same.
Yeah.
Okay. I have one more question for IT Delhi. So what was your reason for why not E?
Why E couldn't form?
Yeah. What was your reason?
So, in the first two cases, we had a free NH2 group along with the base that could do the isocyanide reaction, but in the last nucleophile, the free NH2 was not there, so that this reaction could not happen.
Okay.
So what is isocyanide reaction?
I think this is the isocyanide reaction. I'm forgetting some reagent, but this is the broad of what
Methyl
happens.
is coming. So where from that methyl is coming?
Yeah. So I think it should come from. I think CH3. I don't remember actually.
Okay.
So I would like to call KMC Gopal Pramanik to present the answer.
For the mechanism of formation of A, they were kind of right. There are two aromatic electrophilic substitutions, but after that, this dehydration mechanism is wrong. So basically, there is protonation of this oxygen. So this will go off, another cation will be formed, right? That will be attached to this one. That is fine. So then you will not have a OH here, right? And then this can get protonated. This will create a plus, and this will cyclize again. Okay, so that is basically the formation of A. And then B is basically you have added POCl3, which is a chlorinating agent, so that is COCl, no problem. But the problem is that this isocyanide reaction does not happen with NH2. This happened with CH2N2, right, which is diazomethane. That carbon is the source of the carbon in the isocyanide. But anyways, so basically you have added a hydrazine. So here chlorine is a better leaving group, right? So there is addition elimination with this NH2 and H2, which is similar to the product IISc has done. And so you have NH and H2, which is basically B, and sorry, C. And then D will be, so you have this imidazole derivative here, right? Now you have to look at which of the nitrogens have the most electron density, right? So now if we draw the structures, then this nitrogen has the most electron density by this one. And also if this electron is in conjugation, this nitrogen is the one which has the most electron density. So this nitrogen will basically do the nucleophilic addition elimination. And after that you will get whatever the R group that exists, that's your D. And E is also similar, just that here you will have CH3 in place of NH2. Okay. And then to 3. For the 3, IISc was a bit closer. So basically this is the ring we have in ET2. If you look at this ring in A, there is a benzene ring here and the same in ET2 here itself. So there is this COH, right? Now in pH 5 it's pink. In pH 5 it's pink because there's a extended conjugation between these two benzene rings, right? But at pH 8, which is slightly alkaline pH, this will deprotonate and make you CO minus, right? This CO minus can attack here and make this quinoid go into benzenoid form. So this will regain its aromaticity, this benzene ring and this benzene ring, but there is only one cost, that is this benzene ring will be in conjugation with itself, this will be in conjugation with itself. There is no extended conjugation which is giving you the colorless nature, right? And then you have added copper 2 plus. Now the problem there is basically of bite angle. So the two nitrogens, IISER has shown that these two will complex, which is wrong, right? Because this is smaller bite angle. So the complexation with this will be like this one, but that will not give you the desired UV visible peaks, right? Because the UV visible peak of acidic solution of A, which is basically the form which is drawn in the paper, that has a characteristic peak at 490 18 m, right? So basically we are getting back A after the whole mechanism. So after this chelation has happened, this coordination will increase the rate of hydrolysis by water itself, right? So the water will attack and basically undo whatever you have done from A to D. Now point is that when you have Ag2 plus, so oxygen, we know that this is a hard center, right? Oxygen and nitrogen. And copper 2 plus is also hard. But when you go to Ag2 plus, that is softer. So the interaction is lesser, the coordination is lesser, so the rates are slower. That's basically the part. And then E does not have the chelation as they mentioned, but again, with not the same ones.
So I'd like to hand over the mic to Ahon.
Thank you, Aditya. IIT, yeah. IIT Kanpur, please choose your question. Turn me on like a light switch, I see. Being a chemist of many talents, Samriddha works in the fields of macrocyclic and low-valent chemistry. A fresh set of publications got his lab a prestigious grant, which he used wisely to buy new silver and rhodium compounds. Working on the following thiophene-based framework, Samriddha synthesized the following series of compounds through the given scheme. The scheme is provided. Identify the first question is identify the compounds A, B, and C. It was found that the IR spectrum of compound C shows the presence of a CO double bond with a peak at 1688 centimeter inverse. Investigating the photochemical properties of these compounds, Samriddha irradiated C with UV light with lambda equal to 290 nanometers, which resulted in it converting reversibly to compound C prime with the corresponding C double bond of stretching frequency increasing to 1716 centimeter inverse. The second question is explain this change in the C double bond dose stretching frequency. Additionally, he investigated the catalytic properties of his compounds, utilizing A as a catalyst for the transesterification reaction given in scheme 1, and B for the hydroboration of terminal alkenes given in scheme 2. In both cases, he observed that the rate of the reaction decreased significantly when the reaction mixture was irradiated with UV light. So K UV and K non-irradiated are the rate constants for the reactions with and without UV light respectively. The third question is, help Samriddha explain why the rate of catalysis decreases with UV irradiation. Also, identify the step in the catalytic cycle for the hydroboration reaction, which is affected the most by the UV irradiation. The catalytic cycle is given below. So IIT Kanpur, do you have any clarifications regarding the question? Okay, then your time starts now. 5 minutes remain, IIT Kanpur.
Okay, so in the reaction that forms A, we believe that a fluorination reaction will occur in some way. And then for B, a similar sort of like a chlorination reaction can occur. Now for the second part, as was said, the CO bond stretching frequency will decrease. So hence the CO bond becomes weaker, the bond energy reduces. We believe that this might be because of there being some amount of resonance in C dash, which gives rise to other canonical forms, causing the reduction in the CO bond energy. And then moving on to the last part, then the catalytic cycle for hydroboration. We believe that because of UV radiation, there will be some kind of free radical formation, which might hinder the step of alkene coordination. So, yeah. Okay. Yeah. What do you want to say? We have 2 minutes.
2 minutes remain.
What do you want to try for C? You answered 3. I answered. We're done with 3. We done? Okay. Yeah, that's it.
One clarification for the question, for all questions, the reactants given in parentheses are solvents. Thirty seconds remain. Time's up.
So for the catalytic cycle question, we think the step which is affected by UV irradiation most is the removal of ligand L part, because in without it, so we observe the reduction of rate when it's irradiated, which means if that L is not removed, so this cycle would never happen. And since this cycle introduces more step, instead of boron directly going on double bond, so this reduces the rate overall. So that's why we think removal of minus L in the first step, this RHL cube Cl to minus L, is the rate limiting step.
And yeah, in the case of C dash, because the amide H is negative, we assume that there is a reaction of N with CO, and on UV, on irradiating it with UV light, there is like one bond breaks. As a result, there is lesser conjugation of N with C, and the CO bond length increases. As a result, stretching frequency increases.
For the compounds A and B, we
30
think,
seconds left.
Since AgI is like removes as a salt, hence forming complexation as similar to given for the Ag2O case. So for the A part, we think AgI will remove, and so it will donate it as a ligand.
Time's up.
Okay, so for the stretching frequency part, as stretching frequency increases, the bond order should decrease, and we feel like it is stabilized by the nitrogens. Like if we form the singlet state when UV wave is radiated, the singlet state is stabilized by the lone pair of nitrogen, hence the frequency increases.
For the last part in the catalytic cycle, we think that the UV radiation will affect the addition of the alkene coordination step the most, because it will create free radicals which will then act as a ligand for the rhodium metal.
And like for the structure of A, it's since it's a fluorinating agent, we see the precipitation of AgI, and like there's an plus a positive sign here and an F minus in surrounding.
IIT Bombay, your time is up.
Yeah. So in problem 3, the rate of catalysis decreases with the UV irradiation. The reason is this UV radiation can cause this nucleophilic electron density to break up into two radicals, so that would inhibit this alkene's ability to attack. So the step that would be affected the most is the alkene coordination step, in which this alkene replaces the ligand. Okay, so this
IIT Delhi, your time is up. Do the judges have any clarifications from the teams?
Yeah, I see. So can you clarify? You talked about the structure of A. So can you just write that again and say what happens?
The structure of
A. E. No, just A like apple. A.
Since like we assume PF6 is a very stable species because it's sterically hindered, so AG plus will be removed Yeah, so Ag plus will combine with AgI and it will be a salt with this compound and PF6.
Okay. Another thing, you said in the catalytic cycle, the limiting step is, you assume that the limiting step is the removal of the ligand.
Yes.
And that's why the catalysis slows down. Now, why do you think it is, why is, whatever, this leaving happening not as efficiently when you irradiate?
Because we observe that during the cycle itself, the ligand L wants to join in with rhodium. So I think it's more stable to have ligand with the ligand in the complex. But for this cycle to happen, ligand need to be removed somehow.
Yeah, correct.
So basically, I think
No, so but why does it, I think the question is, why does the rate decrease with UV radiation? Okay.
Yes, sir.
So what is UV radiation doing, which is slowing it down?
yes. So
Which is slowing down that, let's assume that that part is correct, that,
yes, sir.
that your rate determining step is fine and it needs to break the ligand, okay?
Yes, sir.
Now, why will that be slower if it is UV irradiated?
Yes, sir. So if UV radiation is not there, this if we think that ligand that step ligand removal is not possible, so we won't go through this cycle for the whole process, because we want to do hydroboration. So directly boron will react with the double bond, but since now there is the whole complex, so it's sterically hindered, so the reaction would be slower, and like it also goes through a whole cycle.
Okay.
So that's
So
why-
UV versus non-UV, what is the difference, you think? What's the key difference?
So initially we have this LHRHL3 Cl, and to that we need to form RHL2Cl. But if UV was not there in the process, then this ligand won't be removed. So we are missing this for doing our cycle. So we won't be going into this cycle.
Okay. You have anything to ask? Okay, fine.
I would request QMC Upal to come on stage and present the solution.
Okay, so, okay, yeah. So mostly thing is that I have to explain everything from this first. So I'll draw it here. So the first case, you have this salt, which is the iodide salt, right? And you have added AgPF6, right? PF6 minus bulky anion cannot coordinate. So basically you have AgI precipitating and PF6 outside, right, as a counter anion. So basically whatever was there earlier, that is there, just the anion exchanged. Double bond plus thiophene, this one. Okay, that is A. Now in the case of B, you basically have this species coordinating to AgI, right? Coordinating to Ag plus. So this species, as you can see, that there before this step there was a carbocation, right? And then this has become a donor, so it has got a pair of electrons. Earlier there was none, right? So that pair of electrons, so basically this carbon is 6 electron species, right? And so this is a carbene which is donating to Ag plus. So now you have added this rhodium quadchloride dimer. Now if you look at the rhodium is at oxidation state 1, because there's only one chlorine like this, right? And there's same species, there's a dimer. Now this chloro is a bridging in the case of rhodium quadchloride, the metal precursor. Now here the carbene which is formed in the previous case, AgI will precipitate and the carbene will coordinate to rhodium itself, right? So basically that would have this carbene in H and whatever was there earlier. So that is B, and the C is basically a sheaf based condensation. So C was the easiest one to get actually, which is similar to the structure IIT Bombay has written, but then things changed. Okay. Now the point is that for the next part of the question, we have asked that why the CO stretching frequency changes. Now, as they asked for clarification, I say that how many COs are there? There is only one CO in the compound. So this stretching frequency we are talking about, this will help you guide what UV irradiation does, right? So basically, as we see that the nu bar is increasing, right? So nu bar is basically 1 by 2 pi into root over of K by M. So K is the bond strength, right? So basically, if the bond becomes stronger, then the nu bar increases, right? So basically, after UV irradiation, the bond is stronger. Now look at this ring. This thiophene and this thiophene, they are not in the same plane, right? They are away from each other. That's why this is dashed on this one. This is planar, but they are not in conjugation with this ring, right? This is planar by itself. So basically, this lone pair was always in conjugation in C itself, right? Now, when you have this UV irradiation, this bond, which was earlier partially double bond character, that is becoming more of double bond, right? Why? Because then this conjugation of nitrogen's lone pair with the CO, that has to break off, right? So the only way that is going to break off is when this bond moves out of this ring, right? And so there is a cyclization which will happen. So this photocyclization is what is happening in all of the cases. Whenever you add UV radiation, this photocyclization happens. And what that is essentially does is that involves the nitrogen's lone pair in conjugation outside the ring. So it cannot donate with the C double bond O, which leads to a stronger CO bond and effectively higher stretching frequency. And in 3, there are 2 mechanisms to explain. One is for the hydroboration scheme 2, and for the scheme 1. So basically the first one is transesterification step, right? So basically you have an ROH, which is basically this allyl alcohol, right? So you have added tertiary butoxide, potassium tertiary butoxide. It's a really good base, right? So this O minus picks out the hydrogen and it creates the alkoxide, right? This alkoxide can again attack to your ester. So attacking here, this goes out. So you'll get this intermediate which will have all these things. OCH2, this thing. This species you will have. Now, in the previous case, when this was present, this is the A, right? With PF6 minus as the counter anion. When you UV irradiate, then this bond is going to go out, right? There's a double bond here. This will cyclize again, right? Which will increase the positive charge here. So this O minus, this intermediate which is formed, that intermediate can attack here, right? Because this is basically an octet stable carbocation. So this can attack here and that actually consumes all the intermediate. So as the intermediate concentration never rises up, the process does not go forward in UV, right? And in the third case, so if you look very closely, if you have drawn the structure of B, then basically you would have seen that this complex we have, that is actually RHL2Cl, not L3Cl. There's one ligand, which is the cod, there's one chloride, and there is one carbene, right? So now RHL2Cl, that goes into the hydroboration mechanism. So now what in irradiation is happening is that this position will become more and more electron deficient, right? So that pulls the electrons from rhodium. So the rhodium actually at the end becomes more and more electron deficient, right? So when oxidative addition happens, 2 groups adds to it, so it's fine. Alkene coordination and the L which is removing, the labile ligand will be removed, right? Because in the quad you will see that there are 2 alkenes which is coordinating to here. Only one can coordinate, it's always fine, right? So this whole quad can go out in the case of alkene coordination. And the next case, that can again join out. But the only problem which is there is in the reductive elimination. Because in the reductive elimination, 2 bonds are being broken. So a rhodium carbon bond and a rhodium boron bond. So as 2 bonds are being broken, more electron deficient the species, that species will rather slow out the step as UV is irradiated, right? As in this case, when it has cyclized. In the case of the cyclized product, so this carbon is more electron deficient. That tells you that the rhodium becomes more electron deficient. So the rhodium will not want to break the bonds. So the reductive elimination becomes slower and so the rate decreases.
Thank you, Upal, for the explanation. I hand over the mic to Aditya.
Thank you, Ahon. So IISc Bangalore, please choose your question. Caged joy. Here is the question. Happy, a Khushi cage chemist, was trying out the following scheme to produce supramolecular assemblies with interesting properties. Cage compounds are characterized by three-dimensional structures which have a defined rigid geometry. The cages formed 1 and 2 have approximately equal age lengths, where exactly 6 equivalents of the PD complex react with 4 equivalents of the respective tripyridyl triazine to form the cages. Question number 1. Draw the schematic structures of the cages 1 and 2. Happy wanted to study the effect of the cages on the given reaction between hydroxymethyl anthracene and N-cyclohexyl melamide. Initially, she performed the reaction without the cages, first at a lower temperature and then at a higher temperature, which yielded compound A. The yield of A was higher at a higher temperature. Happy was khushied at this and wanted to see whether compound 1 would help increase the yield. However, the joy was immediately caged because another product B, which is a structural isomer of A, was also formed when 1 was used along with the reactants. However, when she used compound 2, the rate of formation of A increased. The entire scheme is as follows. Yields are reported 24 hours from the start of the reaction. Question number 2, draw the structures of A and B. Question 3, explain why heating provides a higher yield of A. The next question, give a plausible reason for the formation of B. And the last question, explain why catalytic amounts of 2 increases the rate of formation of A. So IISc Bangalore, do you have any clarifications to ask? Please ask him. IISc Bangalore, are you done? Your time starts now. Just one clarification, the three-dimensional representation as a schematic is fine. Just mention where the things go where.
So for the first part, where we need to find the structure of the cage.
5 minutes remaining.
We think that for the one, it would be straight prism-like structure because all the n are on opposite side and they are symmetrically placed. But for the second one, since n are not exactly on the para position, they are on the meta position and they are like rotating. So we think it would be kind of rotating. It would be kind of rotating like prism. So basically, it will have a triangular base, and then in between there will be 4 of our n groups, and for the straight one there would again be a triangular base above, and then they are joining. But for the rotating one, we think this one will be rotated. Now for the A and B, we think since there is only heating, we think it's Diels-Alder reaction with so our A is रुक जा एक सेकंड, ये शिट थोड़ी गड़बड़ हो गई। अरे ये गलत है। ऐसा ऊपर आता होगा।
IISER Bangalore, 2 minutes left.
Yeah. So it will be a Diels-Alder reaction. A will be from this diene and B will be from this diene. We observe A without the cages because this is the most it will form the most stable. It will form the most stable compound, and the yield increases on heating because Diels-Alder reaction become faster when it is heated. But we'll have B when we add 1 because it will catch this molecule. So the side positions won't be available for adding. So we can add only to the middle diene. So we'll get structural isomer of A, which is B, and for the fifth part, we think there is a catalytic rate increase for the formation of A.
30 seconds remaining.
Because now it catches it, but its bottom position is available because the structure is rotated, so it can add to the bottom now. Structure problem.
IC Bangalore, time's up.
So we'll have again Diels-Alder reaction in this, but we can have two types of Diels-Alder reaction. One will create a 4-membered ring and one will create a 6-membered ring. To create a 6-membered ring, we'll have to consider a resonating structure of the second compound. We're drawing the product A over here. This is the cage structure for the first part.
Okay, so it looks like a tetrahedral structure with this sort of forming on a face of a tetrahedron. The two faces are connected by the PD complex. So this is the rest of the structure. Yeah, so the PD connects to these, and there is the N over here. So these connections are on the 6 sides of the tetrahedron. The second part is also similar, with just the connections happening a little on the side instead of the midpoints. And yeah, so this is the first and second cage structure for the tetrahedron cage which is forming.
As for why heating provides a higher yield of A, so when we heat the compound, the Diels-Alder reaction can happen more easily because we are having a lot of bond breaking and bond formation going on, and so it will provide the required amount of energy for the reaction to proceed.
And why catalytic amounts of to increase the rate of formation of A, because it is a cage structure. So
Time's up.
Yes, so the structure we think that is at the corners, there will be the big compound that we have here, and it will form simply like a tetrahedron, but
Time's up.
little.
Okay, first off, for the third part, heating provides a higher yield of A because the reaction must be endothermic. So since the delta H of the reaction will be positive, so heating would actually increase the yield. For the formation of B, since we are adding the cage structure 1, it might be that some kind of rearrangement occurs because of which we get a structural isomer of A. When we add 2 in catalytic amount, since A is a cage, some nucleophile might be caged because of which the yield of A increases. I really don't have much to say. Thank you.
So IIT Delhi, do you want to really revise?
Time is up. So yeah, you can ask the question, sir.
Yeah. So do you want to really revise your A and B? Something is missing in that, no?
Could you repeat the question?
Do you want to revise your structures A and B? Because many
Oh yeah, so
carbons
that
are
OH group is missing. That CS2OH.
You want to write
Yeah.
revised structure?
Yeah.
Still they are not correct.
Okay. I think I think that's all.
That's all? Okay, thank you.
Yeah. So IIT Bombay, you said that you said that's a tetrahedral structure of the cage, and but you said something like there's 6 sides of the tetrahedron. So the palladium are, do you think? Because there's no 6 sides, no, of the tetrahedron. So
There are 6 edges. So the palladium.
6 edges. Acha, you meant edges?
Yeah.
Okay, you said the palladium was sitting on the 6 edges of the.
Yeah. So each face has a this nitrogen compound, and it's connected by the palladium edges at the edge.
Palladium edges. Okay, got it. That's what you meant. Okay, okay. Okay. Yeah.
So I would like to request KMC Jagdish to present the answer.
Yeah, hello. So first I'll draw the cages. In the first case, your cage will actually look like an octahedron. Okay. However, you don't have all the sides of the octahedron filled because you have only 4 of your ligand. So essentially, it looks something like this. I'll just redraw it. Okay, so in this case, in the bottom half, the opposite planes will be filled, and in the top half, these 2 planes will be filled, will be occupied. So the projection of it will look something like this, with your PDs looking over here. This is one plane, one phase of your cage. And in the second case, it will look slightly different. And that is, it will become a ball in this case. Why is that happening? Because of the positions. So okay, and the 4 triangular faces will form over here, and the projection in this case will look something like this. So in that case, the PDs were at the edges, at the corners, but here the PDs will be at the edges. So if this is one case, the adjacent phase will have this PD and this PD common, and similarly on the opposite side, the same 2 phases will, so it's symmetric essentially. Okay, so this is part 1. Once you get part 1, the next parts are easy. So A and B, regular Diels order. So in the first case, it will hit in the central ring, and this is thermodynamically more favorable because you are forming 2 benzene rings, which is better than 1 naphthalene. And you have your OH. Okay, this is A, which is the more favorable
product, which is why you see A in all the reactions. However, B, so this is the case. So in case of B, you will form the Diels-Alder at this end. So you'll end up with this. So this is my B. Okay. Part 3 is why does heating. So heating, so in Diels-Alder you'll see that the 2 pi bonds are broken, and in return you get 2 sigma bonds and 1 pi bond, which requires heat, so energetically more favorable. And on top of that, it increases the the chances of random collision between your reactants. So higher yield in case of heating. And why is B formed? So B is formed when you have this cage, the first cage. Okay. And in this cage, for your Diels-Alder to occur, you do not have enough space inside the cage because it can't hit from, so therefore it can't hit the central ring, and it has to hit from the side, which is open. So you can see that these 2 faces are open and these 2 faces are open. So it will hit from the side, and therefore the thermodynamically lesser favorable product, which is this, is also formed. Okay, so this is why B is formed. And the last part, explain why catalytic amounts of 2 increases the rate of formation. Sorry. Sorry. Yeah.
This is correct.
Yes. One more double bond. Yeah. Okay. So in the last part, you have A that's having a very high yield in presence of 2. So 2 is nothing but this bowl, right? So first of all, it holds your reactant in place, which increases the chances of the reaction to take place, first thing. And second thing, which is also quite cool, is that once this A is formed, A is formed, you'll see that this carbon, which was sp2 before, is now sp3. And this OH, which was initially planar, becomes like a tetrahedral region. This carbon is tetrahedral now. And therefore, it kind of pops out of the bowl, which further increases. So it occupies the bowl, finishes the reaction, pops out of the bowl, and the next reactant comes into place. So therefore, the rate is much higher. Yeah, that's it.
In the cage formation part, there are 6 equivalents of reactants. Yes. But the cages have only you have only shown PD on the cages. Yeah, where is the?
So I'll tell you. My 6 PDs are on each of the corners here. And this PD is actually, it has the ethylene diamine. Okay. Now, in this cage over here, again, you'll have 1 PD over here, on the adjacent face 1 here, and here 1. And similarly on the other side also. So PD, PD, PD. Okay. And you have 6 PDs and you have 4 of these triangles. So 1 here, 1 on the opposite side, and 2 on the top. So you have 4 triangles. Clear? Thank you.
Thank you, Jagdish. I would like to now pass the mic to Ahon.
Yeah, thank you, Aditya. IIT Bombay, you're left with penicillin 2019. COVID-19 was never going to give us up in 2019. However, Dhritiraj, our savior, did not let us down. Working to save his friend Pen from the coronavirus, he studied various derivatives of penicillin 5 and their effects on inhibiting the main protease enzyme, or MPRO, of the SARS-CoV-2 virus. MPRO is a key enzyme of coronaviruses and has a pivotal role in mediating viral replication and transcription, making it an attractive drug target for SARS-CoV-2. The efficacy of these penicillin derivatives is measured by their half maximum inhibitory concentration, IC50, which is defined as the concentration of a drug required to inhibit a biological process by 50%. Dhritiraj found the following values of IC50 for these derivatives of penicillin. All values of IC50 are for a 0.15 micromolar solution of SARS-CoV-2 MPRO, whose active site is provided. So you can see the various penicillin derivatives and the active site of the virus, of the enzyme. So question 1 is, provide a possible mechanism for the inhibition of SARS-CoV-2 MPRO by A and give the structure of the deactivated enzyme. Question 2, compare the IC50 values of A and B and explain the difference. Question 3, when compound C was used instead of A, the IC50 value was over 50 micromolar. Why is this so? Question 4, behind the higher value of IC50 for compound D as compared to compound A. In an effort to develop a facile synthesis for the penicillin derivatives, Dhritiraj treated the compound F, given below, with tert butyl oxychloride, resulting in the formation of G. Now question 5, work out a plausible mechanism for the formation of G. Does the team have any clarifications? Okay, then your time starts now.
Because they said that there's a Dean's order reaction. They also said that there are two different process sites. So out of 3 marks, again half. They didn't give any structures, the first team. They also said that it will be faster when heated. That's also correct. That is 2 marks. That I've given total 3.5 to the first team. 0.5. 0.5, see, because I gave this part that said has 3 marks, okay, which is to give the Dean's order structures, one with the central ring and one with the side ring. They didn't draw the structures, but they said it is that central ring and side ring. So out of 3, I given half, 1.5 marks. For the white is faster, they said if it is heated, it will be faster. So that has 2 marks in this marking scheme. The cage joiner, second part. Why is it faster when heated? That they answered correct. Why the heating provide, yours will be here. No, that no marks. They didn't get it. So why heating provide, that the answer correct. They just said these are the thermal structures. Okay, no one gets it. Nothing else I have. No, I did.
One clarification, all the penicillin derivatives physically fit in the active site.
Correct. Amount was correct. 4 palladium, 6. That I give some half mark. Yeah. IISER, I gave for the Dean's order, heated is correct, that full 2 marks. To identify these are different structures, 1.5. So total 3.5. Out of this 3, I've given 1.5 because they said that one will add here, one will add here. They didn't write the structure. No one got structure.
साइड भी ड्रॉ करता हूँ. हाँ ठीक है, ये तीन, हाँ तीन फेवरेबल. उसके बाद ठीक है, पहला वाला
उसके बाद अपन ऐसा बोल देंगे since based on this operation
मैं बोलना चालू करता हूँ क्योंकि टाइम लग. बोल दो ना, धीरे धीरे बोलना चालू करो. ऑब्जर्वेशंस बोलता हूँ, ये सब बोलता हूँ. तू भी आ जा, तू भी आ. तू ऑब्जर्वेशंस लिख दे, मैं बोलता हूँ. मैं एक और चौक लिख दिया, मैं एक्टिव साइड ड्रॉ करूँ.
Okay, so over here in our active site, we have two nucleophilic species, which one is the sulfur and one is the nitrogen. On the penicillin, we will react with two electrophilic species to create a cyclic structure. One is the sulfur over here and one is the nitrogen over here. They are electrophilic in nature because of the two double bonded oxygens who will be pulling the electrons, and over here the nitrogen is in resonance, so so its lone pair is also it shows some electrophilic character as well. Now some of the observations are that if we have a 4-membered ring, then it is favorable compared to a 5-membered ring which is obtained in part D. The second is that we having these two double bond oxygen on sulfur is favorable, and also if they are on the same side, that is if the nitrogen and
5
the
minutes
sulfur,
remain, IIT Bombay.
if the nitrogen and the sulfur are on the same side, then it is also favorable for the IC50. So this all leads us to nitrogen and sulfur being the electrophiles, because if we remove, so let's start with the first question. The mechanism is that these two electrophiles will react with these two nucleophiles to create a cyclic structure. The second question, the IC50 values for A and B. In A, both of these bonds are on the same side, and in the active side also, both of the bonds are on the same side. Therefore, it can easily create a cyclic structure. But in compound B, the nitrogen is below the plane. Since they are on opposite sides of the plane, it will be much more difficult to create a cyclic structure. Thus, the IC50 value is much higher. In question number 3, compound C also yields a higher value because we don't have the double bonded oxygens, and the electrophilic character of sulfur will be reduced significantly. Thus, it will not react properly with the active site and disable it. In question number 4, the IC50 value for compound D is again higher than compound A, because this 4-membered ring becomes a 5-membered ring, which decreases the strain, and thus again the reactivity of the electrophile and the nucleophile decreases.
Two minutes remain.
So in the compound that we are given, first of all, TBU OCl will break as OCl minus and TBU plus. OCl minus will attack over here, and this bond will break. Finally, we'll have something like this, where the sulfur bond has break. This is OCl minus, and later the sulfur has a lone pair, and there's a carbon double bond nearby. It won't react with ether, so it will attack on the carbon double bond. The Cl minus will get removed from here. It will form a double bond with oxygen, and then we'll have the final product.
IIT Bombay has finished presenting. Wait for the timer. And time's up.
Yes, so the enzyme is nucleophilic, and all the compounds that we are using it to inhibit it are electrophilic, and formation of the ring would happen. If we compare A and C, the only difference is that the oxygen that was increasing
is not there, so we need a higher concentration of it to for the reaction to happen. And if we compare A and B, so a ring formation can happen in A very easily because they're both on the same side. And if we compare A and D, 5-member rings are more stable, so that compound would be less reactive. So that's why the less is more actually compared to A. And yeah, so that's it for the questions 1 to 4. And this is the reaction. This is the mechanism for problem 5.
Seconds remain.
So the first step, so we can see here the double bond is electrophilic is nucleophilic in nature, and Cl has a +1 oxidation state because of attached to O. So this attacks Cl. Sulfur has a lone pair on it, so sulfur attacks this, and we get a 5-membered ring, which is preferred. Then sulfur can lose this bond because there is the protection of nitrogen lone pair on this carbon. So we do that here. And then since the solvent is moist,
Ideally, your time is up.
Okay, first off, the mechanism for inhibition of the enzyme is as such. So, as we can see, there are the active side. So, what the addition of the following compounds will do is the active side, they'll bind to the active side so that the stuff that actually has to bind there will not bind. So that by making the enzyme inactive and unable to catalyze. So between A and B, the only difference is that this the groups are on the same side versus the groups are on the opposite side. As we can see in the active side, the groups are on the same side, and it will be easier for them to cyclize with groups on the same side, which is why the IC50 value of A is less than B. For A versus C, the sulfur has very less electrophilic character because of the absence of the double bond O's, so therefore it will not be a good agent to react. Versus D, it is a 5-member rings are more stable, so it will be less reactive.
IIT Kanpur, your time is up.
So So for the mechanism of how it is being inhibited, so we need to check how, if the molecule fits or not. So if we try to fit A onto the binding site, the rings will go below the active sites, and the part sticking out tries to come out of the area. So since in the A it's above, it can come out, while in the B it cannot come out. So B is less preferred. Similarly, in the C, the direction is reversed, so it doesn't fit again in the active site. For the part D, since it's a 5-member ring, again it's taking more space, like it's shifting the space inside the cavity. And for how we form by moist THF, basically first N and S bond cleavage happens over there. It forms 2OH. 2OH forms ketone, and Cl positive attacks forming a 3-member ring, and SH attacks on.
Do the judges have any clarifications from the teams?
Yeah, so IIT Bombay, so you said, I think, for between A and D, when you compare the IC values, you said that, there's a difference between 4-membered ring and 5-membered ring, that's fine. But what is the reason you think that the IC value is greater in the 5-membered ring? What was the reason you said?
Since 4-membered ring is less stable than the 5-membered ring, we feel that the negative I effect of minus I effect of 4-membered ring is more than the 5-membered ring. Hence, the sulfur would be more electrophilic in that case. Hence, the compound A will have lower IC50 value.
Okay. So IIT Kanpur, what was your reason for this 5-membered ring versus 4-membered ring?
Our reason for the 5-membered ring versus 4-membered ring was that the 4-membered ring has more angular strain, so I guess the compound will be more reactive.
Anything else? Yeah, okay.
I request QMC Upal to come on stage and present the answer.
So first of all of these penicillin derivatives, they actually physically fit inside. So there's no problem of fitting inside of these ones. Now, the thing is that in the active site, you can see that there is a thiol group and there is a imidazole group, right? So this thiol, this is the nucleophile, right? Now, there are many positions to attack, right? There is this amide position, and there is one thing they have forgot, so this is OPH, so there's a CH2 in between. This position they can attack, this position they can attack theoretically, and this position they can attack, right? Now here, the point is that the nitrogen is not in conjugation with this one, and also this is a 4-membered ring, so there is more ring strain in this ring. So the fast attack is going to be this one, right? So it goes here, this goes back, then this comes here, this N- is formed, right? So this bond is cleaved off. And so what you basically have is here, the S and that whole enzyme. This is the first step. And then this N-, so then this thiol, this is basically S plus and H plus in physiological pH, right? So this H plus can again protonate this one. And so this ring can go off, and you basically have SO2H at the end. And this whole, basically both the rings are open. Now in the case, okay, so now we need to look at how the attack is happening before. So this thiol ring, right? So this is a carbonyl center. So in this carbonyl center, the attacks are at 107 degree, right? Because you need to put your electrons in the pi star of this C double bond O. So it will attack from the back side of this one. So towards the ring, right? So that is only happening if it is from below that attack. Right? So as the attack is from below, here both of the substituents are above. So there is lesser steric hindrance. But in the other case, in the case of B, you see that one of them is towards below side. So the attack is more hindered. And in the case of C, as the oxidation state of sulfur is lesser, so the electrophilic pool is lesser. So the second ring does not break. How does it influence IC50? Because the work of the imidazole is basically, once the whole ring is opened, this phenyl that can do pi-pi stacking with the imidazole ring again. So that is also the thermodynamic reason why C has greater IC50. And then for D, this is a 5-member ring, so the ring strain is lesser. So that's why the attack of thiolate is less favored. And then for 5, okay. So for 5, basically, the thing is that everything depends on the chi values, which is basically the electronegativity values. Now oxygen is most electronegative, then there is chlorine, and then there is sulfur, right? So basically, you have this precursor. Now here you create a Cl plus, basically. This Cl plus can be attacked by this thiol first, right? So first the thiol attacks, you get a SCl plus here. This is the first step. And then there is moist THF. So this comes here, cleaves off this part of the ring, right? So you will have this SCl and one OH here. Now the oxygen will take its lone pair back, and the nitrogen will become N minus, which will be stabilized by the H plus, which is formed here because water is attacking. So you'll basically get this whole part of the ring with itself. And so you will have NH, and then there will be a double bond O, and there is a CH3, right? So there is this SCl which is present in the THF medium, and so now chlorine is more electronegative than sulfur, so Cl minus will form, and so this will cleave off, and you will have the S plus, and that will basically create a sulfonium ion which will add to this case, and the Cl minus that will attack from behind and cleave this trigonal intermediate, which is similar to the bromonium, and so you will get back to your 5-membered ring. And the stereochemistry of this position never changes because there's no attack there. So that's basically the idea. And CH2 Cl. Anything else? No. Yeah, that's all.
Thank you, Upal. The deep thought for chemistry ends here. I hand over the mic to Dipansh to conclude the session.
Yeah. So this is the end of Deep Thought Chemistry. Thank you everyone for being present here. Thank you judges for being present for the judging. Now after this we will be having a brief thought in LHC that will start at 3 p.m. I request every team to reach by 2:30 in LHC. Please reach on time because we have to brief you guys. Also audience is welcome for the brief thought. They can come to the LHC. Now, thank you everyone. For those volunteers who have the volunteers and the our team our participants, please have your food. There is your team coordinators know the place where the food is available. They will just take you guys, and please have the food. Thank you everyone.